So today we're going to cover section 3 and we're going to be using chords. So the first one is a theorem and it's called the congruent corresponding chords theorem. And what this one states that in the same circle or in congruent circles, two minor arcs are congruent, and notice here the words if and only if their corresponding chords are congruent. So what this means is they can either give you that the chords are congruent and then you can conclude that the arcs are congruent, or they could start out by saying if the arcs are congruent, then the chords are congruent. So this can go either way. So you'll either have congruency marks on the chords like in this picture, and then from there you can tell that these arcs are congruent, or vice versa. The next theorem is called the perpendicular chord bisector theorem. And this one states if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So here, if EG is the diameter in this picture, and if EG is perpendicular to the chord DF, then that tells me that HD, this little piece here, will be congruent to HF, and the arc measures are also going to be congruent. So FG or GF would be congruent to the GD or the DG. So these would be congruent arcs here. Next. Okay, so next, again, don't memorize the number. You can memorize the name or what it states. This is the converse of the perpendicular chord bisector. And here, if one chord is a perpendicular bisector of another chord, then we can conclude that that first chord is a diameter. So here, if QS is a perpendicular bisector of TR, then QS is the diameter of the circle. Remember, the converse switches the order, the if and the then. The other theorem on the previous slide stated that if a diameter is perpendicular to a chord, then the diameter bisects the chord. Here, we're telling if a chord is perpendicular bisector of another chord, then it's the diameter. So they switch the order for the converse of the if and the then statement. And then the last theorem is called the equidistant chords theorem. And this one states that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Again, we've got this if and only if, which means it can go backwards and forwards. So here, if you have congruency marks on your chords, AB is congruent to CD, then if and only if, this little segment here, EF, is congruent to EG. So if it's equidistant from the center, then we know that those chords are congruent.
And they'll give you the marks, right?
They're going to either give you marks on the chords or on the equidistant segments. So they can do it either way because of the if and only if. So the chords would be congruent, and so are the equidistant segments for this one. And now we're just going to apply and do examples using these four. The three theorems and then that one. So it wants us to find the values of X and Y in each of the pictures. So let me zoom in here and let's take a look at example 1A here. So notice in this picture, here is the center of my circle. And I've got some radii going on here. So I've got a radius right here, which has 13. Then I've got another radius over here, another radii, and this one's also 13. Because remember, no matter where the radius is in the picture or in the circle, they're always going to be the same measure, and they're all 13. Now, the 5 is for this leg right here. So this part right here is for the 5. And then they're asking us to find x. Notice what we formed here is a little right triangle here. So what we're going to do to find x is the Pythagorean theorem. So we can go ahead and 13 is the hypotenuse. It's our c. So we're going to be doing 5 squared plus x squared equals 13 squared. 5 squared is 25. 13 squared is 169. Subtract 25. X squared equals 144. Square root it. And x is equal to, now normally it should be plus and minus 12, but because this is the side of a triangle, we're only going to keep positive 12. Now, this segment that's right here, let me highlight it in yellow. This right here is the diameter. So in order to find y, we can do two things. If you want to go ahead and draw in another radius, you can go ahead and do Pythagorean theorem again, but it's going to be the same answer because, again, since this is a radius, it's 13. But the faster way to find the value of y is to use one of the new theorems we just learned. And we could use Theorem 10.7, but again, don't memorize the number. It's called the perpendicular chord bisector theorem. So we can use the perpendicular chord bisector theorem to find y. And what this one states again is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So that tells me that x and y are equal. So x is 12 and so is y. Now again, you could have done Pythagorean theorem and you would have seen that you were doing the same thing. Instead, it would have been y squared plus 5 squared or equals 13 squared. Either way here. But the faster way, as soon as you recognize that that diameter is perpendicular to the chord, you know that that chord has been bisected. Okay, so when you have a diameter of a circle and when it's perpendicular to a chord, it's going to bisect that chord and its arc. So it's a perpendicular bisector, in other words. So that would just make x and y congruent because that diameter is perpendicular to the chord. Let's try B. Now this one, in addition to finding x and y, it also up here, notice it wants us to find the measure of arc AB. But let's go ahead and work on finding x and y. Notice the angle measure that's given to us up here, 60 degrees. We're going to reach back to our special right triangle chapter. So if I go ahead and pull this triangle out of here, I'm going to go ahead and do it over here on the side. I'm going to draw the 30, 60, 90. So up at the tippy top was 60. And then down here, this could be 30. And then you have the right angle. So x is here, y is here, and they gave me this side at 6. So here's where we're memorizing the relationship of the sides of the 30, 60, 90. Remember, we memorized that the side across from 30 was a. The side across from the 60 was a square root 3. And the side across from the 90, the hypotenuse, was 2 times a. So in order to find a, which is really going to be my y, I'm going to solve 2a equals 6. Divide by 2, and a equals 3. So y equals 3. And then x is whatever a was with root 3. So x equals 3 square root 3. So this is 3 square root 3. And then this one is just 3. Now, it also wants us to find the measure of the arc. So just like before, we knew that when we have a central angle, so if you think about this, let's see, let me get a different color in here. So 60 degrees right here, this is a central angle. And remember, its intercepted arc, this arc right here, is the same as the measure of the central angle. This is what you did on the quiz yesterday. So this arc measure is the same as the central angle at 60 degrees. And then we just learned the perpendicular chord bisector theorem that states, because I could extend this, because this is a radius here, right here, this is a radius, and I could make it go in the other direction. So this is now a diameter. And since that diameter of the circle is perpendicular to the chord, it bisects that chord, and it also bisects the arc. So if this side is 60, then this side over here is 60. And then arc AB, I can use my arc addition and add 60 plus 60, and this will be 120. So arc AB is 120 degrees.
You knew that.
Notice here, I've got 2 segments that are marked as equidistant from the center. So I got these little congruency marks here. Let's see if I do them in pink. So this is going to tell me I could use that equidistant chords theorem. And I can know that these 2 chords here are going to be congruent. And I also know that if I were to extend this, this is a radius. If I were to extend this, or actually the equidistant, sorry, I know that this has been bisected. So x equals 8. And then this whole thing is going to be 8 plus 8. It's 16. Because this is a perpendicular bisector, and then this is 16. Okay, so I'm going to be using my equidistant chords theorem because I've got a segment, and remember, distance is always indicated by a right angle. So because it's equidistant, each of these chords are equidistant from the center, because I've got congruency marks on them, that's how I can tell that they're equal. Because of that, I can use my equidistant chords theorem, and I can state that the chords are also congruent. This is also a perpendicular bisector, so that's how I knew that if this side was 8, then this side is 8, and then 8 plus 8 is 16 to give me the value of y. It wants me to find the measure of arc CD in the diagram. So over here is CD. It's where the 9x is. Notice, again, I can use my perpendicular chord bisector theorem because I can see that BD here is a diameter and it is perpendicular to this chord. And by the perpendicular chord bisector theorem, I know that this has been bisected, so this is congruent to this, as well as the arc measures. So in order to find for x, I'm going to know that CD, arc CD, is congruent or equal to arc DE. So I'm just going to set 9x equal to 80 minus x, add the x, 10x equals 80, divide by 10, x equals 8. Now it didn't ask for just x, it wanted us to find the measure of arc CD. So now I need to take this 8 and plug it into the 9x. So CD was equal to 9x, so 9 times 8, and arc CD equals 72 degrees. Now, just to modify this a little bit, let's say they asked us to find the measurement of arc BC. BC is over here. Let me highlight this in pink. Realize that the endpoints here, this is actually a diameter here. So this would be a semicircle arc. So if I already found CD, all I would need to do is do 180 minus 72, and arc BC would be 108 degrees. So again, treat these like puzzles. 80 minus x, that is also 72 because x was 8, 80 minus 8 is 72. So they could have either asked for BC or BE, like she said. Either way, these are congruent arcs because, again, they're part of a semicircle arc. Yes. One last example. Careful here. Don't be misled and think, oh, look, I've got a right angle here, and think that 9x should have been equal to 90. That only works when it's a central angle. 90 degrees is not sitting at that center. It's not a central angle. So you had to use the fact that they were congruent arcs to find their measure. So you couldn't have done 9x equals 90. That wouldn't have worked because, again, it's not a central angle. Let's try the next. Yes. Example, and then we're done. So here it says, in the diagram of circle C, QR is equal to ST, which equals 16. So, and it's labeled in the picture. So we have two congruent arcs, QR and ST are congruent arcs. So that tells me by the theorem of the equidistant chords theorem that if two chords are congruent, then they're also equidistant from the center. So that tells me that CU here is going to be congruent to CV. So in order to find the value here, I could say CU equals CV, and I can plug in 2x is equal to 5x minus 9. I'm going to go ahead and get my like terms together. Doesn't matter which way you move it. You just need to get an x on one side and your number on the other. And then now I divide by -3. X equals +3. And it didn't ask me to find x. It wanted me now to find CU. And remember, CU equal to x. So now I just have to do 2 times 3. And the length of CU is 6. So this is 3 examples here that we did using all of the theorems that we just learned. So that is it for the notes on 10.3.